Welcome to our latest video on the topic of orders of reaction and rate equations. This video is suitable for A-level students. By the end of this video lesson, you should be able to understand that a rate equation shows chemists the mathematical relationship that exists between the concentration of reactants and the reaction rate. You should also be able to determine the order of reaction from experimental data and be able to use this data to work out the value of the rate constant K, including units for this constant in your answers. Now, in our previous video lesson, we discussed the concept of a rate equation, and we said that a rate equation shows the mathematical relationship between the concentration of reactants and the reaction rate. So the order of a reaction tells us the exact dependence of rate on concentration, and this slide shows the rate equation. So if we have a reaction A plus B going to products, rate is equal to K times the concentration of A raised to a power, let's call it M, times the concentration of B raised to a power N. Now, M and N are the orders. The reaction order is M with respect to A. It's the power that the concentration is raised to in the rate equation. And the reaction order is N with respect to reactant B, because the concentration of B is raised to a power N. Now, the overall order of the reaction is M plus N. Now, the values that M and N take, the orders with respect to each concentration term, can only be determined experimentally. And the proportionality constant K is called the rate constant, and the rate constant K is different for every reaction, and it varies with temperature. So it must be quoted at a temperature. You have to quote the value of K at a temperature for it to be meaningful, because it varies with temperature. Now, order is simply the power that the concentration of reactant is raised to in the rate equation. So we're going to start this video lesson with a practice question to test your understanding of what you can remember from our previous video lesson. So read through the question, pause the video, have a go at it, and then we'll go for the answers. So this practice question is asking you to consider the reaction between the ester, ethyl ethanoate, CH3COOCH2CH3, and sodium hydroxide. So it's base catalyzed hydrolysis of an ester. Now, you can see from the equation that it would react to form sodium ethanoate and ethanol, and the reaction is first order with respect to the concentration of the ester, and first order with respect to the concentration of sodium hydroxide. And this first question is asking you to write an expression for the rate of this reaction, in other words, the rate equation. So rate is equal to K times the concentration of ester. So we denote concentration with square brackets. So I've got square brackets and I've got CH3COOCH2CH3. And this is times against the concentration of NaOH, because NaOH is also first order. Now, question B says the reaction is overall second order, work out the units of K, and we've already seen it's second order overall because we've written the rate equation. And rate is equal to K times the concentration of the ester times the concentration of NaOH. So to work out the units of K, we just substitute in the units for rate, which is moles per decimeter cubed seconds to the -1. Now that's equal to K times the concentration of ester and NaOH. And concentration is measured in moles per decimeter cubed. So it'll be equal to K times moles per decimeter cubed times moles per decimeter cubed. So we just rearrange this to get the units of K. So K is equal to moles per decimeter cubed seconds to the -1 over moles per decimeter cubed times moles per decimeter cubed. Now we then look to see if we can cancel out any of the concentration terms. So moles per decimeter cubed features on the top and the bottom here, so we can cancel them out. So we'll be left with K equals to S to the minus 1, seconds to the minus 1, over moles per decimeter cubed. Now when expressing the units of K, we need to write this all on the same line. So when we move moles per decimeter cubed up to the top, it becomes moles to the minus 1, dm to the 3, and we also have S to the minus 1. So the units are moles to the minus 1, dm to the 3, S to the minus 1. Now in our previous lessons, we've discussed the concept of rate equations and how we can work out the units of the rate constant K. Now in this video lesson, we're now going to explain how we determine the order with respect to each reactant present in a chemical reaction. And this involves a series of experiments called runs in which the concentration of one reactant is varied whilst the concentrations of the other reactants are kept constant. Now if you study the initial rates of these experiments, it allows the order with respect to the reactant to be determined. And the orders can be found by simple inspection of the data or by plotting graphs. Now at A level, you'll be expected to use the inspection method to determine the orders of each reactant. So now let's look at how the inspection method works. Now this method involves you taking each reactant in turn and comparing at least 2 runs or 2 experiments. And you're trying to find out what effect doubling the concentration of each reactant has on the rate. Now it's important that you make sure that in the 2 runs you pick, the other reactant concentrations remain constant. Now if you double the concentration of the reactant, keeping the other reactant concentrations fixed, and the rate doubles, this reaction is first order with respect to that reactant. And if you double the concentration of the reactant, keeping the other reactant concentrations fixed, and the rate quadruples, so in other words multiplies by 4, the reaction is said to be second order with respect to that reactant. So now let's look at how we work out the order with respect to each reactant. So if we look at the table here, we have different experiments. We have 3 experiments called runs. And if we look at run 1 and 3, you can see that we double the concentration of A, but we keep the concentration of the other reactant the same, 0.2 each time. And when we double this concentration of A and we keep the other reactant constant, you can see that the rate quadruples. And therefore, we can say that reactant A is second order. And that's because when we double the concentration of A, the rate multiplies by 4. So from inspecting the data, we can see that when we double the concentration of A, the rate quadruples. So we can conclude that it's second order with respect to A. And now we have to look at the data to see what happens when we double the concentration of B. Now, if we look at run 1 and run 2, experiment 1 and experiment 2, we're doubling the concentration of B, but we're keeping the concentration of A the same, 0.1 moles per decimeter cubed in both experiments. Now when we double the concentration of B, the rate doubles. Now from this we can conclude that it's a first order relationship, because if you double the concentration of a reactant, in this case B, and the rate doubles, we can conclude that it's a first order relationship. Therefore, as it's second order with respect to the concentration of A and first order with respect to the concentration of B, we can write the following rate equation. Rate is equal to K, the rate constant, times the concentration of A raised to the power 2, times the concentration of B, and it would be raised to the power 1, but we don't need to write the 1 in because it's first order. So rate is equal to K times the concentration of A squared times the concentration of B. And that is our rate equation that we've determined from the table of experimental data. So now we know the rate equation. Rate is equal to K times the concentration of A squared times the concentration of B. all I have to do now is substitute the values from the table into this equation to find the value of K. So I'm going to use the values from run 1 or experiment 1. So if I now use these values and substitute them into the rate equation, I would have 1.6 times 10 to the minus 2, the rate for experiment 1, being equal to K times the concentration squared of A times the concentration of B. So it'd be K times 0.1 squared times 0.2. So 1.6 times 10 to the minus 2 is equal to K times 0.1 squared times 0.2. And if I rearrange this, I can get K. So K is equal to 1.6 times 10 to the minus 2 divided by 0.1 squared times 0.2. Now, if I put these numbers into the calculator, I'll have 1.6 times 10 to the minus 2 divided by 2 times 10 to the minus 3. And that will give me a value of K equal to 8. So now that I've worked out the value of K, all I have to do now is work out the units. So all I'm going to do is substitute the units for rate and concentration into my rate equation and then rearrange it to find the units of K. So moles per decimeter cubed seconds to the minus 1 is the units of rate. And I've got 3 concentration terms in my rate equation. So it's going to be equal to K times moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed. And if I rearrange this, I'm going to get moles per decimeter cubed seconds to minus 1 divided by moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed, which is going to give me K. So all I've done here is just rearrange this equation to find K. So it's moles per decimeter cubed seconds to minus 1 divided by moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed. And then I cancel out, where I can, the concentration terms. So if I do this, I'll be left with seconds to the minus 1 over moles per decimeter cubed times moles per decimeter cubed, which will be moles squared dm to the minus 6. And if we write this all on the same line, we will end up with moles to the minus 2 dm to the 6 seconds to the minus 1. So now let's test your understanding of this with some practice questions. Here's the first practice question. Read for the question, pause the video, have a go at it, and then we'll go for the answers. So the first part of this practice question is asking you to work out the order of the reaction with respect to reactant X and Y. So I'm looking for runs where I double one of the concentrations and I keep the other fixed. So if you look at run 2 and 3, I'm doubling the concentration of X, but I'm keeping Y constant. So when I double the concentration of X from 0.2 to 0.4, the rate doubles. So I can conclude that it's first order with respect to X. Now to work out the order with respect to reactant Y, I once again have to look at the data. And if we look at run 1 and 2, I'm doubling the concentration of Y, while the concentration of X remains fixed at 0.2 moles per decimeter cubed. And when I double the concentration of Y from 0.3 to 0.6 moles per decimeter cubed, the rate once again doubles from 1.6 times 10 to the minus 4 to 3.2 times 10 to the minus 4. So therefore I can conclude that Y is first order as well. So now that we've worked out the order for both reactants, we can write an expression for the rate equation. So rate is equal to K, the rate constant. And remember, when we write K, we need to write a small k to denote the rate constant. And rate will be equal to K times the concentration of X times the concentration of Y, because they're both first order. So now that you've determined the order with respect to each reactant and written the rate equation, we now want you to work out the value for the rate constant K, including units, with your answer. So read for the question, pause the video, have a go at it, and then we'll go for the answer. Now, to work out the value of the rate constant K, all I need is the rate equation. Rate is equal to K times the concentration of X times the concentration of Y. And then I just substitute in the values from one of the runs. So if I use run 1, I have a rate of 1.6 times 10 to the minus 4. And that is equal to K times the concentration of X. And the concentration of X is 0.2 in run 1. Times the concentration of Y, which is 0.3. So if I rearrange this, K is equal to 1.6 times 10 to the minus 4 divided by 0.2 times 0.3. And therefore, that is 1.6 times 10 to the minus 4 divided by 0.06. And if I put these into the calculator, I would get a value for K which is equal to 0.0026. Now I must include units with my answer. So let's now work out the units. So the unit of rate is moles per decimeter cubed, seconds to the minus 1. So I'm going to write this up here because I've got more space. And the unit of concentration is moles per decimeter cubed. So moles per decimeter cubed, seconds to the minus 1 is equal to K times moles per decimeter cubed times moles per decimeter cubed. Now I can rearrange this to find the units of K, because moles per decimeter cubed, seconds to the minus 1, which is the units of rate, is divided by moles per decimeter cubed times moles per decimeter cubed. And then if I cancel out the concentration terms here, one on the top and one on the bottom, I'll be left with units of K equal to seconds to the minus 1 over moles per decimeter cubed. And if I write this on the same line, it will be moles to the minus 1, dm to the 3, seconds to the minus 1. And that would be my units of K, and my value of K would be 0.0026. So I'm going to write my units in here by my value, 0.0026 moles to the minus 1, dm to the 3, seconds to the minus 1. So here's a second practice question for you to have a go at, and this question is in a number of parts, and the first part is shown on this slide. So read for the question, pause the video, have a go at it, and then we'll go for the answer. So question 2a is asking you to work out the order with respect to iodide ions and H plus ions for this reaction. So once again, I'm looking for values where I change the concentration of one of the reactants and I keep the others fixed. So if we look at runs or experiment 1 and 2, I'm changing the concentration of iodide here from 0.01 to 0.02, but the concentrations of hydrogen peroxide and H plus ions remain fixed. Now when I double the concentration of iodide ions, the rate quadruples. It times is by 4. So therefore I can conclude that it's second order with respect to the iodide concentration. So now I know the order with respect to I minus. I have to look at the order with respect to H plus. So to do this, I look for experiments where I change the concentration of H plus ions, but I keep the other concentrations fixed. So experiment 2 and 3 allows me to do this. And when I double the concentration of H plus, keeping the other concentrations fixed, there's no effect on the rate. The concentration change does not affect the rate. So therefore, I can conclude that when I double the concentration of H plus ions, there's no effect on the rate. So therefore, it's zero order with respect to H plus ions. And if it's zero order, we don't need to include H plus ions in the rate equation. as they don't affect the rate. So now have a go at parts 2 and 3, read through the question, pause the video, have a go at it, and then we'll go for the answers. So in part 1, we worked out that it's second order with respect to I- and zero order with respect to H+. Now the question tells us that it's first order with respect to hydrogen peroxide. So when writing the rate equation in part 2, we write down that rate is equal to K times the concentration of H2O2, hydrogen peroxide, times the concentration of iodide ions raised to the power 2, because remember it's second order with respect to iodide ions. So rate is equal to K times the concentration of hydrogen peroxide times the concentration of iodide ions squared. And part 3 is asking you to calculate the rate constant K for this reaction. Now I can use any set of data here to work out the value of K. I'm going to use experiment 1, but I could use the values in experiment 2 or 3. So I'm going to use all these values in experiment 1, and I'm just going to substitute them into the equation. So rate equals 1.15 times 10 to the minus 6, and that's equal to K times the concentration of hydrogen peroxide, 0.010, times the concentration of iodide ions squared, so it's 0.010 squared. And I can rearrange this to find K, so it will be 1.15 times 10 to the minus 6 divided by 0.010 times 0.010 squared, and that will give me K. So therefore K is equal to 1.15 times 10 to the minus 6 divided by 1 times 10 to the minus 6, and that's 0.010 times 0.010 squared, and that equals 1.15. Now remember the question is also asking you to state the units for K. So to do this we just substitute in the units for rate and the units for concentration. So it would be moles per decimeter cubed seconds to the minus 1 over moles per decimeter cubed times moles per decimeter cubed times moles per decimeter cubed. And that would give me the units of K. Now if I cancel out the concentration terms here, I'll be left with seconds to the minus 1 over moles per decimeter cubed times moles per decimeter cubed, which would be seconds to the minus 1 over mole squared dm to the minus 6. And if I put this all in the same line, I'll end up with moles to the minus 2 dm to the 6 seconds to the minus 1. And that would be my units, and my value would be 1.15. So here's our last practice question, and here's the first part of this practice question. So read for the question, pause the video, have a go at it, and then we'll go for the answer to the first part of the question. So this question is looking at the reaction of an ester, methyl ethanoate, with water to form a carboxylic acid and an alcohol. And the question is asking you to define the rate of reaction. Well, this is the change in concentration of reactants or products with respect to time. So we can write this as the change in concentration of reactants or products over the time taken. And this is because it's a change in concentration of reactants or products with respect to time, and concentration is usually measured in moles per decimeter cubed seconds to the minus 1. So here's the next parts of this question. So read through the question, pause the video, have a go at them, and then we'll go for the answers. So for this question we have the reaction of an ester with water, and they give you the rate equation and they give you a table of data, and they're asking you to determine the values of x and y here, which are the orders in the rate equation. So if we look at the value of x, we're going to look at changing the concentration of ester and keeping the concentration of hydrochloric acid the same. So if we look at the first two experiments here, that's what happens. And when we double the concentration of ester, the rate doubles. So therefore, we can conclude that the reaction is first order with respect to the concentration of the ester, methyl ethanoate. So the value of X will be 1. Now to determine Y, the order with respect to the HCl, we once again look at the experimental table, and I'm looking at experiments where I change the concentration of hydrochloric acid, but I keep the concentration of ester the same. So I've highlighted these experiments I need to look at here. Now when I double the concentration of hydrochloric acid, the rate doubles from 1.68 times 10 to the minus 6 to 3.36 times 10 to the minus 6. So because I double the concentration of hydrochloric acid and the rate doubles, I can conclude that the reaction is first order as well with respect to the hydrochloric acid concentration. So the value of Y is also 1. So there's 2 marks for this question. So you get 1 mark for the correct value of X and Y. Now part 3 says, given your reasons, explain the role of hydrochloric acid in the hydrolysis of this ester. Now you'll notice that hydrochloric acid appears in the rate equation but not the chemical equation. So that instantly tells me that hydrochloric acid is a substance that affects the rate of reaction here, but it's not part of the chemical reaction. It's not used up in the reaction. So therefore, it must be a catalyst. And I know this because any substance that's present in the rate equation, but not the chemical equation, is a catalyst. So I'm just going to write down that HCl is in the rate equation, but not the chemical equation. I get 1 mark for saying that. So therefore, it must be a catalyst. 1 mark if you mention it being a catalyst. So that concludes this video lesson. So after watching this video, you should now understand that a rate equation shows chemists the mathematical relationship that exists between the concentration of reactants and the reaction rate. And you should also be able to determine the order of a reaction from experimental data and be able to use this data to work out the value of the rate constant K, including units for this constant in your answers. So that concludes this video lesson. So please check out our YouTube channel, Dr. O Chemistry, which has lots of GCSE, AS and A-level videos, and our Twitter site @RadaChemistry.